Alright, in this tutorial we're going to look at series circuits by basically applying Kirchhoff's loop and junction rule to a simplified version of what we've already seen. And then in the next tutorial we will look at the cousin, if you will, parallel circuits. Key thing to keep in mind is that the rules for series and parallel circuits are what we've already learned in terms of the loop rule, the junction rule, as well as Ohm's law. The only thing that's going to be different here is how to deal with multiple resistors and calculate resistance. Alright, so otherwise things should be fairly straightforward. So let's take a look at our circuit that I have as an example. So we have a series, we have 1, 2, 3 resistors in series. And how do we know that they're in series besides being told that? Because there's only one path from the positive to the negative terminal. Okay, so no matter which way you go from positive, negative, positive, you must pass through each one. As such, we should be able to easily see how the junction rule applies here. If I've got 2.4 amps right there as labeled, then I have to have 2.4 amps, 2.4 amps, 2.4 amps. And so what we can basically say about anything in series is that the current in any part of the circuit equals a current through each part. Okay, sorry they got run through there. And why is, again, it's the Kirchhoff junction rule, which is really just the law of conservation of charge. Alright, so the common mistake to make is they see that this has a resistance of 2 ohms and this has a resistance of 3 ohms, so you want to say this one has more current in it because of Ohm's law. Ohm's law still holds here, but what you're assuming in this is the voltages are the same. That's not the case because of the loop rule, which we'll talk about in a second. So if we want to start filling in the chart that I have here, you were told that the current circuit is 2.4 amps, so we know that the current through each resistor is also 2.4 amps. That's a given for a series circuit, irrespective of their resistances. That's really important to keep in mind. Okay, now let's apply the loop rule. Well, we got how many loops from here to here in a series circuit? Well, there's just one loop. So the loop rule tells us that the EMF is what's set up, and that's got to equal the drops across each one. So we can call that V1 plus V2 plus V3. And why, again? That's Kirchhoff's loop rule. So we can do some, perhaps, figure out what is going to be the voltage drops across each one if we know their resistances. So if we know that R1 has a resistance of 2 ohms and we know that the current is 2.4 amps, then we can multiply the two and we see that there's a 4.8 volt drop here out of the 24. For R2, it's simply 3 times 2.4, which is going to be 7.2 volts. Now for R3, we don't know its resistance yet, but we can actually figure out what it must be, knowing now applying, going down on here. So if we go across on this chart, this is a really handy chart to do, you can apply Ohm's law. When we go down on here, we are doing the Kirchhoff's junction rule, and going down, and on this column we would do the loop rule. So we know that this plus this has to add up to that. So V1 and V2 are 12, so V3 must be 12 volts because 12 plus 12 has to give us 24. Okay, so that's really nice. Now that we know that V3 is 12 volts and the current is 2.4 ohms, we can divide the two and we can get R3, which is 5 ohms. So what I want you to understand, I know I'm moving quickly here, is an interplay between Ohm's law when we go for any particular row, and then the junction and loop rule for any particular column. So that leaves us, well, what about resistance? How do we deal with resistance? If I've got a 2, a 3, and a 5 in series, what does that give us as a whole? The common sense would say that they should add up to 10. Well, does that follow from Ohm's law? Well, let's see. If I've got 2.4 amps in a circuit for 24 volts, then my effective resistance is the overall resistance that the circuit feels. I don't want to use the word total resistance for reasons we'll talk about later. So we'll call it effective resistance. Well, by applying Ohm's law, voltage divided by current gives me 10 ohms. So sure enough, the effective resistance is the sum of the three. So we can write that. That's an important equation. the effective resistance of a series circuit is simply the sum of the individual resistors. Okay, I could do a formal proof of that. I'll save that for class. Okay, but we can see from the grid why that must work out from Ohm's law and the matching. So this is really nice. Now power, how would we calculate the power through each bulb? In other words, if I ask you now which bulb is going to be most powerful, the least resistance, the most resistance, or are they all going to be the same? Okay, before you do any calculations, you might want to think about that and come up with an answer before I solve this. All right, hopefully you have a solution. Let's work it out. There's a lot of different ways I can calculate each power. I can do V squared over R, I can do I squared R, I can do V times I because I have all that information. I'm just going to do V times I for these, even though my numbers aren't perfect. So I got 4.8 times 2.4. So that's 9.6 plus about 3. So I'm guesstimating here. This is about 12 point something watts. Okay, I'll let you work it out. For I2, I've got 7.2 times 2.4, so that's 14, 16.8, plus another, let's call it about 17 point something watts. And then if I do 2.4 times 12 volts, 12 times 2 is 24, and that's about 28 point something watts. So we can see that the one with the most resistance has the most power. This goes against what we talked about with simple circuits, where we said if you want more power, you want less resistance. So we'll explain why that is a little bit. Now let's go across here. Our overall voltage is 24. Our overall current is 2.4. So 24 times 2.4, let's see, that's 48 plus an additional about 10. So that's about 58 watts. Let's see if I did any of my math right. If I add these three, they should add up to around 58, 20, 30, 40, 48, 55, 57. So adding down and doing the power equation across tells us that. Okay, so you want to be able to do a grid like that, but more importantly, what you want to recognize is that the voltage drops add to the whole, and we can get the individual voltage drops by doing Ohm's law across. And then the currents are all the same, irrespective of the resistance. Okay, so that's how we can explain Ohm's law now. So let me come back to that. Why doesn't this have more current than this? Because it doesn't have as much voltage. So if I apply Ohm's law to this, I'll have a smaller voltage divided by a smaller resistance. Gives me the same thing as a bigger voltage divided by a bigger resistance. So it's all consistent. Alrighty, so let's look at just a few little related problems before we stop here. Okay, what would happen if another resistor were added to the circuit? And we're going to assume it's added in series. So I can go back up here and let's say I put some R4. All right, I don't know its value, but it doesn't really matter what it is. Okay, what's going to happen to the effective resistance? In other words, is the circuit going to feel more resistance, less resistance, or the same amount? Well, effective resistance goes by the sum, so what we would add here is an R4. R1, 2, and 3 don't change, so the effective resistance would increase. That should be pretty clear. So a general rule, the more resistors you put in series, the more resistance you get. Okay, what would happen to the current then? Well, according to Ohm's law, our overall current is equal to the EMF divided by the effective resistance. Okay, so I'm not looking at the individuals, I'm looking at the whole. So our EF is the potential across the whole circuit, and the effective resistance is what the circuit feels as a whole. So EMF stays the same, but effective resistance went up, so the current would decrease. So adding more resistors gives us more resistance, therefore less current. Okay? Therefore, the voltage drop across each resistor would have to do what? Well, voltage drop is I times the individual resistances. I has just decreased for the circuit, so therefore it decreases for each individual resistor. So the R has to, or I is less for the same R's, so the voltage drops would have to decrease. And that kind of makes sense from another standpoint, the loop rule, if you were thinking perhaps. If I've got a total drop of 24 for the 3, if I add a fourth one in, it's not like there's nothing remaining for that. The circuit adjusts, in a sense, the current so that the drop across here decreases, decreases, and then there's some left over for R4, and such I still get 24 volts. I'm not going to do all the work, but if I were to tell you R4 was, let's say, 3 ohms, you should be able to readjust this whole chart here and everything would work out. Okay, and therefore, here's the most interesting thing. What would happen to the power output? Well, the EMF, the easiest way to approach this is the power output for the circuit is the EMF times the current in the circuit. The EMF hasn't changed, but the total current has gone down, so the power output would decrease. So if we were dealing with light bulbs, putting more light bulbs in series gives you less brightness, less power. That's not why you usually put more light bulbs in a circuit. So in your home, if you have a chandelier and you're putting more and more light bulbs in it, and you get more and more brightness, that tells you they're not in series. Okay. What can be inferred about the resistance of any ammeter? Okay, so let's think about it. I'm going to draw a simple little circuit here, right, with one resistor in it. Now I put an ammeter. So when I connect an ammeter, it's automatically in series. Okay? So if I put the ammeter in series, because that's how it has to be connected, I've got two resistors in series with one another. Okay? Do I want the ammeter to affect the resistance of the circuit? If it did, it would affect the current, and then my measuring device would affect the thing it's measuring. That's a no-no. So what that tells us is that the ammeter must be essentially zero resistance. Otherwise, it would increase resistance. Thus, it would, increase, but it would affect is maybe a better term I want here. Therefore, it would affect the current and the voltage and the power. So if the ammeter has some resistance to it, it changes everything that's measuring, and you're not allowed to do that. So remember this, ammeter must be in series because otherwise it can't measure current. And if it's going to be in series, we don't want it to affect resistance, then it has to have essentially no resistance. And the last one, I have two light bulbs, a 40 watt and a 100 watt. Which one is brighter? Well, if we put them in their own circuit, the 100 watt bulb is lower resistance. We learned that. Therefore, more current, and therefore more power, right? It's 100 watts. But what happens when I put them in series? Okay, so imagine I've got a 100 watt in series with a 40 watt. And we just learned that this has a small r. That's why it's a bigger one. This has a big R. Okay? Well, if the 40 watt has a greater R, but it has to have, because they're in series, they have to have the same I. That's the junction rule. So if this has a bigger R, but the same current as the 100 watt, then it has the greater drop in potential. And if it has a greater drop in potential, then it has a greater power. So weirdly enough, if you take a 40 and you put it by itself compared to 100, this is less bright. But when you put it in series, because it has greater resistance, it's going to have more power because the putting in series equals out the current. So what that assumes then is when you plug in a light bulb in a circuit in your home and then you replace it with a 100 watt, they're not connected in series, they're connected somehow else, so the voltage is the same across them, but not necessarily the currents. Okay, so this concludes series circuits. We'll pick up the next one on parallel circuits.